The next example we have here, a rope of length 0.75 meters has a small weight of mass m equals 0.1 kilograms attached to the end. If the rope is spun in a circle at a rate of 120 RPM, what acceleration is the weight experiencing? All right, dealing with rotation with circles, we know we have a few types of acceleration we should consider. There's centripetal acceleration, so what's actually keeping the weight on the circle. And then we have our angular and tangential acceleration as well. So is it speeding up or slowing down as it rotates around the circle? To kind of understand if we have that information, we want to read our problem again. And it mentions that it's circling at a rate of 120 RPM. And there's no mention of change from that. So this is our angular speed, and it's constant. Okay, which is good for us because it means that the angular acceleration and the tangential acceleration are zero. So we don't have to consider those. The only acceleration in this case is going to be our centripetal acceleration, keeping our object on the circle. And from before, we know centripetal acceleration is v squared over r. And so you're welcome to use this 120 RPM. We could convert that to the linear speed, and then we could go ahead and solve for the centripetal acceleration that way. However, I want to show you kind of an alternative way to think of the centripetal acceleration. Remember that we defined v as omega r. So if we substitute in omega r in the place of v, so that's omega r, all of that squared over r, we can go ahead and simplify this. So omega squared over r, or omega squared r. And this gives us, like I said, a different way we can calculate the centripetal acceleration. If we know that angular velocity, then we don't have to go through that extra step of finding the linear velocity from that. And so that's how we'll go ahead and solve this one. The one other thing we need to do, the rate that we're given, the velocity is 120 RPM. And RPM is revolutions per minute. Revs per minute. But as we know, our SI unit is radians per second. So we want to go ahead and convert this number, 120 revs per minute, to radians per second. And I like to, when I'm doing these unit conversions, I like to split up my units very clearly into a numerator and denominator, because it'll make kind of canceling things out a lot more straightforward to look at. So we could start with our time. We need minutes to cancel. So in 1 minute, there are 60 seconds. And that way minutes will cancel out. We'll be left with seconds in the denominator. And then I'm going to go ahead and multiply on our unit conversion for revolutions to radians. So in 1 revolution, there are 2 pi radians. And so we will be left with radians per second once these units have canceled out. When we multiply this, we get omega is 4 pi radians per second. All right, and so that's what we can use over here to calculate our centripetal acceleration. So AC equals omega squared r. Omega was 4 pi. We're going to square that whole thing and then multiply it by the radius of our circle. And that's going to be the length of the rope, because the rope is spinning, the full length of that is the radius of our circle. So 0.75. All right, just multiplying this out, looks like 12 pi squared meters per second. Meters per second squared there. And then we could go ahead and multiply in that pi squared as well. It's about 118 meters per second squared. And again, that's the acceleration toward the center of the circle. It's not saying that it's speeding up or slowing down, just that it's changing direction.